So, as we all know, the natural numbers that we considered in the previous lecture uh, are perfectly sufficient to count, but they're not sufficient for our purposes. In particular, from a point of view of arithmetic operations, you will not be able to do all possible arithmetic operations if you only have natural numbers at your disposal. So let's look at this in more detail. If you take two natural numbers and you add them in a usual way, we do it, then clearly the outcome is going to be a natural number, right? If you add two positive integers, you end up with a positive integer. So addition of natural numbers is well defined if you only know about natural numbers. We would say that the natural numbers are closed under addition, meaning precisely what I just said, that adding two natural numbers gives you a natural number. But on the other hand, if we try to introduce differences or subtraction, maybe introduce them in such a way that the difference between two numbers a and b is a natural number, such that b plus a minus b is equal to a, as I'm stating here, then again, clearly I should be able to do this when a is greater than b, right? Because then adding a natural number to b will produce, there exists a natural number or positive integer that I can add to b to get a. But if a is less than b, then of course there is no positive integer that I can add to b to get a. And so if again I'm dealing only with natural numbers, then this procedure is undefined. And also if I cannot add a number to a to get a, because the set of natural numbers does not have zero. So in order to make subtraction possible, we have to extend the definition of a difference to include also a being less than b. And for that, we have to enlarge the set of natural numbers or positive integers to the set of all integers. So you have to include now both positive and negative integers as well as zero. And then, in that case, it's very easy to convince yourself that that the set of integers will be closed under both addition and subtraction. One other thing is that the set Z is strictly larger than the set N. N is a subset of Z. So what we just did, we actually extended set of natural numbers to a larger set for all integers. Okay, so now if, again, we're only aware of operations of addition and subtraction, then a set of all integers would be perfectly sufficient. But then, when we start looking at multiplication, multiplication is just fine. Again, if I take two integers and I multiply them the way we always multiply them, then the outcome is going to be another integer. So clearly the set of all integers is going to be closed under multiplication. So it's now closed under addition, subtraction, and multiplication. But just like as clearly, z is not closed under division because numbers of the form 1/2 are not going to be elements of a set of all integers. So we have to do another enlargement. Now it is an enlargement of z by introducing the set of all rational numbers, where we define rational numbers simply as a pair of integers written in this particular way. So you just write it as m line n, as we always do, where m and n are two elements of a set of all integers, and as usual, the denominator is not equal to zero. So at this point, I'm simply defining Q as a set of pairs of integers. But then this set will become interesting once we can describe, first of all, what exactly is a relationship between Q and Z, because I'm claiming that Q is an extension or an enlargement of Z. And for that, if I just say that I have a set of all pairs of integers, then how is that related to a single integer? So I need to relate these objects m over n to the elements of Z. So then we need to prescribe a set of simple rules which allow us to provide that association and more, actually. So first, we say that if you have two numbers, two rational numbers, m over n, and another rational number which looks like km over kn for some integer k, then those two numbers must be the same. And actually, let me just add something. Oops. Something here. We want k to be an element of Z. Okay, so there are infinitely many ways to represent a single rational number. This is something that we're not going to touch in this class, but there is a notion of equivalence class, which says that you have a whole class of objects m over n that represent the same integer. But that's besides the point here. All right, the second property that we need to relate these fractions to 0. So 0 divided by any n we associate with 0 in a set of integers. Now, we associate m, a pair, m1, or m over 1 with m. So this immediately provides a connection to the set of all integers. We can define in the usual way the multiplication of two rational numbers, the addition of two rational numbers, and we can define what we mean by a reciprocal 1 over a rational number. Once we define the reciprocal, then by taking a product of a reciprocal with another number, we define division. So let's see. So from 3, it follows that Z is a subset of Q, right? Because I can take any element of the set of all integers, write it as Z over 1, and then that gives me an association between an element of Z and an element of Q. So in that way, Z is a subset of Q. We can also say that, going back to 1 for a moment, that if m and n in your fraction, so there are infinitely many representations of the same fraction, but there will be one that is irreducible, right? The irreducible fraction corresponds to writing m over n as by using a pair of numbers where m and n do not have common factors. So I'm just reminding you that there is this irreducible representation of every rational number. Okay, and so then once again, it would be easy to check in this case that the set of rational numbers is going to be closed under addition, closed under subtraction, closed under multiplication, and closed under division. So I will leave it up to you to verify that, but this is sort of an obvious fact. So then it might appear that Q is perfectly nice set of numbers which is sufficient for almost everything that we can do. And indeed, if you, let's say you're counting money, then that would certainly be sufficient because you'll be able to describe excess of money, lack of money. So you have negative sum, then you don't have enough money. you can describe products, divisions, whatever. But this is not really a completely sufficient set of numbers for practical applications, because certain operations are still missing. And one operation that is missing is an operation of taking a square root, or more broadly, it's an operation of, it's not really an operation, but you have equations that you need to have, algebraic equations that you need to solve. And just from the fact that Q is closed under basic arithmetic operations, it does not necessarily follow that you should then be able to solve any equation if only rational numbers are available to you. So, as I'm saying, the deficiency of Q, immediate deficiency of Q that you actually are familiar with, I'm sure, is that if you're trying to solve equations similar to the ones here, then there is no guarantee that the solution of this equation will be a rational number. And if there are no rational solutions, then that means that if I'm restricted to elements of a set of rational numbers, then equations like the ones that are circled on the screen will actually not have any solution whatsoever, right? So, as you know, in fact, that the numbers like square root of 2 and square root of 17 are not rational but irrational. So that means that rational numbers, while they are sufficient for certain purposes, for other purposes you need to extend the set of rationals. There are other deficiencies that the set of rationals have. So besides the fact that certain equations cannot be solved in it, there are other problems that I will describe in the next lecture. But for now, let's try to figure out a systematic way of showing why equations like this are not going to have a rational solution. And for that, I'm going to introduce some terminology, and then we'll prove a theorem. So, if I have a number r, I'm going to call that number algebraic if this number satisfies a polynomial equation with integer coefficients. So what does it mean? It means that for this number r, there exist n plus 1 coefficients that are all integers, such that r solves a polynomial equation with these coefficients. So then square root of 2 is going to be an algebraic number. Why? Because clearly it solves an equation x squared equal to 2, which I can write as x squared minus 2 equal to 0, and that is a polynomial equation with integer coefficients 1 and 2. In the same way, if I have a number like this, written using roots and additions in this case, then I can show that this number is also an algebraic number. How can I do it? I can start squaring to get rid of roots, and that will give me the desired outcome. So let's see, if r is equal to the square root, then by squaring both sides, I get that r squared is equal to 1 plus cube root of 15. Then I'm going to isolate cube root of 15. It's equal to r squared minus 1. So now if I take cube of both sides, then r squared minus 1 cube is equal to 15. So all roots are gone. And I'm going to just distribute and collect all terms on one side. So by taking a cube, I'm going to get this. This is equal to 15. Bring 15 on the other side. Again, this is a polynomial equation with integer coefficients. So that means that this number r is algebraic. Okay, and so now we have the following theorem about algebraic numbers. So suppose that I have an algebraic number. So this is called the rational zeros theorem, the statement that I'm going to make now. Suppose I have an algebraic number r equal to p over q. So this number is not just algebraic, but it's also rational. And I'm going to assume that this number is written in an irreducible form, so that p and q do not have common factors. Okay, because this number is algebraic, it satisfies an equation like this with integer coefficients. And I'm going to assume that the first coefficient an and the last coefficient a0 are all non-zero. And the theorem says that in this case, it will be true that p, the numerator of r, is going to divide a0, and q, the denominator of r, is going to divide an. And so that is the thing that we are supposed to prove here. Okay, how can we do that? We take r as it is given to us, it's p over q. I know that it solves this equation, so if I substitute r into this equation, the equation is satisfied. So r is p over q, so I get an p over q to the n for this factor, an minus 1 p over q to the n minus 1 for the second one, etc. And because r satisfies the equation, then what I get is an identity that this is equal to 0. Now, q, of course, the denominator of my fraction r should not be equal to 0, and it is not. So then I'm allowed to multiply this equation up here by q to the power n. And if I do that, then let's look at the first term. In the first term, I have p over q to the power n. That's the same thing as p to the n over q to the n. If I multiply by q to the n is gone. In the second factor, I have n minus 1 p to the n minus 1 divided by q to the n minus 1. So if I multiply by q to the n minus 1 will disappear, and I just have q left. And if I proceed in the same way, then the remaining terms will look like this. And clearly, for example, a0, if I multiply by q to the n, I'm going to get this. And now I'm going to do a couple of manipulations with this. Manipulation number 1 that I'm going to do, I see that the first n factors here all have p in it. They all have a common factor of p to the first power, right? Because the last guy only has p. So if I factor out p out of them, then this equation double star will take this form, and I'm going to take a0 q to the n and move it on the other side like this. Okay, so then I have a product of two things on the right and two things on the left. There is this complicated parenthesis, but it's multiplied by p. So that means that overall, the left-hand side is divisible by p. And if the left-hand side is divisible by p, and because I have equality, the right-hand side must be divisible by p. All right, so if it is divisible by p, then as we know, if I have a product of two integers, right, q is an integer, q to the power n must be an integer. So through two integers, a0 and q to the n, if the product is divisible by p, that means that either the first number is divisible by p or the second number is divisible by p. Now I'm claiming that the circled number, q to the n, cannot be divisible by p. And indeed, what did we assume about p and q? That this fraction is irreducible. If the fraction is irreducible, then p and q have no common factors. So then q to the n and p also cannot have any common factors. So q to the n cannot be divisible by p, which only leaves me with a0 that should be divisible by p. And that's exactly one of the statements of my theorem. It says that p should divide a0. So this part is proved. Let's do the second thing now. So I can do the same thing that I just did with double star, except that if I look at the last n terms, they all have a common factor of q. Common factor of q to the first power, which I can pull out. And then by moving things to different sides, this is what I'm going to get. And just like in the previous case, we see that the right-hand side is going to be divisible by q. If the right-hand side is divisible by q, then the left-hand side must be divisible by q. Left-hand side has an and p to the n. P to the n I cannot divide by q, again, because there are no common factors between p and q. So an must be divisible by q. And so that means that I established both statements of my theorem as written here, so the theorem has been proved. And now let's talk a little bit about particular examples of how we can apply this theorem. So let's do example number 1. Square root of 2 is not rational. How do we show that? So again, I'm going to let x be square root of 2. If x is square root of 2, then x squared is 2. And then if I move everything in one side, x squared minus 2 must be 0. So that's the equation that I'm working with. So this is equation with integer coefficients. So I can apply rational zeros theorem to this equation. So I'm going to assume that x is rational. What does it rational? What does it mean that it is rational? It means that there exist integers p and q such that x is equal to p over q. All right. Then, by rational zeros theorem, what do we have? Rational zeros theorem says that an, in this case, an is a coefficient in front of x squared, right? So it's the highest power. Let's see. So an, q divides an, right? So an in this case is equal to 1. So q divides 1. And p divides a coefficient, divides a0, right? So a0, the coefficient without x here, is minus 2. So p divides minus 2. Now, okay, so what can I conclude from this? If q divides 1, then there are only two possible numbers that can divide 1. Q can be either plus 1 or minus 1. P divides minus 2, therefore P can be what? Which numbers can divide minus 2? Plus or minus 1 will divide minus 2, or plus or minus 2 will divide minus 2 and nothing else. Okay, so if this is true, then what are my possible choices of P over Q? So P and Q both can be 1 with plus sign or minus 1. So it can be plus or minus 1. P can be plus or minus 2, Q can be plus or minus 1, again with any combination of signs. So their option is plus or minus 2. So therefore, because X is P over Q, X is plus or minus 1 or plus or minus 2. Okay, now we check. Are those actually the numbers that are going to give me 0? So, however, plus or minus 1 squared minus 2 is equal to minus 1, right? Which is not 0. And plus or minus 2 squared minus 2 is equal to 2. So therefore, neither choice of X satisfies x squared minus 2 equal to 0. So therefore we have no rational solutions. And finally, therefore, radical of 2 is not rational. Now let's do another example of a similar kind. Oops. And let's actually borrow from the example above. So I want to show that this number is irrational. Is not rational. Okay, so we already showed that R satisfies an algebraic equation like this. So therefore, let's assume R is equal to P over Q. Oops. Where P and Q are integers, and the fraction is irreducible. Okay, so then by rational zeros theorem, just like in the previous example, what do I know? I know that P divides 1, and, okay, let's see, P divides 16, and Q divides 1. Let me double check because I always forget this. Yes. Okay, so therefore, what are possible choices of P and Q? Q certainly can only be equal to plus or minus 1, right? Because only plus or minus 1 will divide 1. And at the same time, P can be what? Plus or minus 1 will divide 16. Plus or minus 2 will divide 16. Plus or minus 4 will divide 16. Plus or minus 8 will divide 16. And plus or minus 16 will divide 16. Okay? And so what you do in this case, then what are the possible choices of R? Because we're dividing, so R equal to P over Q, because we're dividing by plus or minus 1, then R will have the same values as P. So we can just copy those. And now, just like in the previous example, what we need to do, so if R is rational, then those are the only, the things listed here are only possible choices of what a rational solution of this equation might be. So then what you need to do is, it's a tedious calculation, but you need to plug in all of these numbers into the equation and make sure that the equation is not satisfied. So let's see let's check a couple of them. So if R is equal to plus or minus 1, and then because in this polynomial I only see even powers of R, then having plus or minus doesn't matter, right? So then if I plug this in, I'm going to get 1 to the 6 minus 3 times 1 to the 6 to 1 to the 4 plus 3 times 1 squared minus 16. That is minus 15 not equal to 0. So R equal to 1 is not going to work. If R is equal to plus or minus 2, then what do we have? 2 to the 6 is 2 to the 5th is 32, so it's 64. Minus 3 times 2 to the 4 is 16. Plus 3 times 2 squared, so 3 times 4, and minus 16. So how much is that? 64 minus 48, 16, minus 16, 0, so this is 12. Again, not equal to 0. And you continue by plugging in the remaining numbers 4, 8, and 16, and the outcome will be the same. So there are no, but you have to check this, right? So you have to test all of these numbers. And so then the outcome is that there are no rational solutions to the polynomial equation. And so R is not rational. So you're going to do more of these examples as a part of your homework. And for the next lecture, we will switch then to real numbers. We'll demonstrate what the difference between real and rational numbers is going to be.